Electronic design means designing what you can't buy.
From EE Tech and All About Circuits, this is Moore's Lobby. I'm your host, Daniel Bogdanoff. Today in the lobby, I'm joined by Mike Engelhardt from Qorvo. Mike is best known for creating the SPICE analog circuit simulators LTspice and QSPICE. Qorvo has a free download of QSPICE, hosts a community forum, and has their high-performance silicon carbide models available now. This conversation with Mike was one of our keynotes for EE Power Day, so you might hear a reference or two in there, but people liked it so much, we thought we'd bring it here for you, the podcast listeners, as well. So let's get right to our conversation. Mike, thanks for being here. I'm really excited to have you on the show.
I appreciate the interest. Thank you very much.
I have to say, we're going to get to LTspice in a moment, but I would not have gotten through electrical engineering school without that SPICE simulator, so thank you. How did you first get into technology, and what got you excited about tech?
Well, it was TV, not the electronics inside the TV, but the programming, because, you know, I was from an agriculture region, and the natural thing for me to do would be, you know, some type of manual labor, and I was afraid of being able to live that way. I didn't know if that was going to work at all. But on TV, there were these guys in these crumpled lab coats, these rocket engineers, and they were clearly doing okay, and everybody respected them, but they could hardly speak English. I mean, they were clearly nobody's nephew, and I figured, that's my meal ticket. I could do that. So that's actually why I got into technology. I figured I figured it'd be a way to survive.
So you didn't have to necessarily know the right people or be related to the right people to get into it. It was a way out of manual farm labor for you. That's interesting. Yes. How did you first get into simulation and programming and design?
Well, I started with simulation a very long time ago. It was in 1975. I was at a cyclotron lab, and my project there was doing a relativistic kinematic analysis of a P-alpha reaction, and I wrote this program to do a crude verification of the calibration of the mass spectrometer that was used in the greater experiment.
Today, simulation is just kind of a way of life. There's, you know, we talk about digital twins and all that, but what sort of system were you running on originally, and what was sort of the reaction of people when they saw that you were working on sim tools?
Well, the actual computer that I wrote that in was a Science Data System Sigma 7. It had a reputation for being good at floating point. Myself, I didn't benchmark mainframes as a teenager. Just not what I did. But it was written in Fortran, which I wish I'd not had learned Fortran, because there were better options of that day. I mean, PL1 would have been the language to learn. It offered, even in 1975, it supported structured programming. I would have been much better off and had probably a stronger career in software had I started with PL1 than Fortran. So that's that. You know, the machine was all the normal 1970s stuff: punch cards, exotically noisy printers, you know, line printers, wonderfully air-conditioned rooms. You know, to escape the heat, you just try to find something to do in the computer room.
Fair enough.
You know?
Yeah. So what was people's reaction to simulation and focusing on that? Was that a common thing to do, or was it kind of like, oh, he's over there working on that?
Well, at a national lab, that sort of was the norm. It was not a thing that you were going to do simulation or computation. That's what everybody was doing. So you were either you know, there engaged, or you were not. So that was very much a science thing. That was not engineering. Where you know, engineers have had trouble adopting simulation. You know, particularly not knowing what it was for. But in science, you know, there was no confusion between There's no confusion what the point of with simulation. It was very clear there all the time, and they were never confused about it. And they always were able to distinguish Mother Nature from theory, and they knew how the two should interact. Where engineers are not that good at that.
Interesting. Yeah, we try to build our own frameworks sometimes. So you're working on cyclotron, simulation and data. How did you get into electronics?
I continued on in physics for all of my academic career, and my role in physics labs was to design the electronics and build the electronics that you couldn't buy. So physics experiments, have all these particle detectors and all this other, they use a lot of electronics, relay rack after relay rack after relay rack of electronics with, foot deep cabling between them, and you can't buy a lot of that stuff. You have to build it. So my job was to design and build the electronics that you couldn't buy, which in retrospect, I think is a really excellent way of learning electronics, because ultimately electronic design means designing what you can't buy, or designing what you need from what you can buy. That's the role. So you have to read all the application notes, read all the data books, see what's available, and then jigsaw piece the parts together.
That's kind of the fun of electronics in many ways, is you have this set of discrete tools and parts and chips that all have to play together, and none of them are typically designed specifically for what you want to do, but you got to compile them all together.
So I talked about what got me into electronics, and electronics and electronic simulation are very different. I had a fairly straightforward path into electronics because of my experience designing electronics in physics labs. Which requires a lot of, you really exercise your thought process. You have all this out of the box thinking you have to do. And you really learn analog electronics as the kung fu that it is. Okay, but electronic simulation was a much more, I meandered into it. I didn't take a direct path to it. My first simulators were all for charged particle optics. Starting at the cyclotron lab, and I also wrote a number of simulators for charged particle optics of different applications. And probably the most successful charged particle optics simulator I wrote was for scanning electron microscopes, and I would ray trace the electrons through electromagnetic fields acting as lenses, and then computing the aberration coefficients of these objectives. And I wrote the simulators for that. And there was a number of successful objective lenses designed with those tools that I developed. And then I moved into electronics through oil exploration. See, because salts don't dissolve in oil, and after you're down 1,000 feet below ground, all the water is salt water. It's all conductive. So oil is actually located by measuring the resistivity of the formation. All the oil you've ever used was located because of its resistivity. That's the way you find oil. I wrote a simulator for locating oil, and SPICE was a component in that simulator. And also in that work, I would design a lot of electronics that would work downhole. And these were discrete bipolar designs, and I would curve trace all these electrons. And I just got to a point where I thought I was pretty much at the front of understanding SPICE simulation and what SPICE was doing, from designing, circuits that work far beyond the military temperature range. Designing circuits that have a service temperature of 200 C.
Oh my goodness!
That was the sort of circuits I designed. That was all SPICE simulation and curve trace data that I'd taken myself, and that's how I got involved in simulation was for oil exploration.
So is that the origin? Go ahead. Sorry.
Huh?
Yep. I was going to say, so is that the origin of LTspice? Is that how it came to be? It was for oil?
I would say no. I did have an idea to drop the high temperatures. Well, the trouble with oil is there isn't very much of it in California. So even though I found it a very interesting field, despite the fact that people like to have a bad opinion of oil people, there's so much money involved in oil that to this date, the most smartest people I ever found were in oil. They weren't in, IC design or anything else. There's just so much money involved with it. Money is no object in anything to do with oil exploration. But there just isn't very much of that tool design in California. But there is a lot of IC design. And since I felt I understood SPICE very well, I got involved with IC manufacturers. And I thought that the way to leverage what I could do and what was against what was needed locally would be to write a SPICE program, but not try to sell it like an EDA company, but to use it to sell the electronic components. Team with a semiconductor manufacturer, because if you're going to sell the software, you're one guy writing the software inside of a framework of a company that has to license it to all these people, and they're going to gross $3 million a year, about or thereabouts. But I could be one guy in an IC manufacturer. Instead of grossing $3 million a year, I would use this tool to sell billions of dollars of ICs. And that was the idea behind LTspice, and that's why I wrote it.
Do you think that was also its staying power, is that it was not an EDA tool for EDA tool's sake, but it was a tool to actually translate into the real world and move actual silicon?
Yes, for a couple of reasons. So we're dealing with some relatively new fields here. Numerical methods is from the 1960s. The FFT is considered the dawn of numerical methods. 1960s wasn't that far ago. It's not like it's not like literature, which has a whole history. So we're dealing with fairly new fields, and software project management is a very new field that a lot of people don't understand. And if I knew that I could deal with a million-line code, and the way I would manage the project is to simply fix every bug as soon as it comes up. And if you could hold this million lines at a state of zero outstanding bugs for month after month after month, then eventually you get to a point where a user is statistically more likely to win a state lottery than find a bug in your million-line code. And EDA companies or any software company just doesn't get that. And holding the code in that state is easy if you're the guy that wrote the code. If you don't have that person, then you can't do this. Then you need all this, what they used to call case tools and project manager tools and all these people to try to police how this process works. But if you wrote the code and you get the bug reports yourself, you can get to that point. It's actually not that hard. It's the natural way of doing it.
I can
so
hear.
Those are
yeah. Go ahead. Sorry.
The pieces of the jigsaw puzzle that made LTspice what it was.
I can hear thousands of software program managers screaming in terror at the idea of no bugs in a million-line code.
But the solution is to get rid of them. I know, but what it is.
Yeah.
Hey,
don't comment.
It's all in the name of progress.
Yes, 100%. Speaking of progress, what were some of your early roadblocks and biggest challenges as you were starting to roll out this concept of circuit simulation?
The hardest part of the biggest roadblock, the very most difficult thing, was getting people to understand what was the point of simulation. Okay, this is where I mentioned this at the very beginning, that engineers don't understand the relationship between, Mother Nature, the actual what's happening in hardware, and their theory. Mother Nature doesn't care how you think about what you're thinking in your head. It's not interested. Anyway, the point of simulation, they didn't understand what simulation was for. And the point of simulation is so that you understand the circuit better. And engineers had never been sufficiently introspective to understand that their intuition of circuits design was the most valuable thing they had. Okay. And I would have to contrive these examples that would jolt them into realizing that intuition was the most important asset they had, because that kind of goes against the idea of memorizing a bunch of equations about how Mother Nature works. Okay, so anyway, the example I would, the most effective example I contrived was to say, hey, look, just think back to Europe 1,000 years ago. people collected in cities, and these cities developed, a level of wealth and things and animals, and and other people outside the city wanted all those things, that wealth, and they wanted to come in and attack it. So they would build walls so they could hold, they would defend the city with walls. And an arms race developed. They would make siege machines to defeat the defenses of a city wall. And some of these siege machines were pretty simple. A ladder on wheels. If they had smooth enough terrain up to the wall, they could just push the ladder against the wall, climb it, and hopefully get to the top. But some of these machines were very insidious, and one is a counterposed trebuchet. It's a very sophisticated machine, and people might look at this and say, well, no intuition is required. It's all F equals ma. Can't push a rope, can't pull water. Completely described by Newtonian mechanics. You do not need intuition to understand how a counterpoised trebuchet works. Except that Isaac Newton came about 700 years later. They didn't have F equals ma. Those machines were built by intuition. There's no other explanation. Okay, and so anything you can do if you want to be at the cutting edge of an arms race or any kind of market race, you have to develop your intuition and get it as sharp as possible, and and expand your experience base as best as possible. And that's what simulation does. Okay, and in today with multi-layer boards and surface mount components, it's very difficult to rework a board. And so there's absolutely no way you can understand your circuit as well as you can in simulation as you can with working on the actual hardware on the bench. And that was the hardest thing to convince people. Getting people to understand what the point of simulation was actually extremely difficult. I had people try to codify against what I was saying, that no, intuition's nothing. Simulation has to be more than developing intuition or it's worthless. They say, no, you have to be able to verify a design. Well, you can't verify a design because, you don't have production scatter in your components. And that was the hardest thing. Getting people to understand what the point of simulation was. It was not easy. And it was a struggle that went on for years and years and years.
I'm really happy to hear you say that, because I kind of had this habit in college where I felt a little bit guilty, where I would go into LTspice, and I would pop some components in, and I would just play with parameters until I got the output I want and try and get a feel for how an op amp worked. And doing that on paper was okay, but I felt like I never really fully got it until I was in the tool and adjusting things. And I felt kind of guilty about that, because it should have just been do the math, get the answer. But to hear you say that it's about intuition development makes me feel a lot better, 15 years later. So thank you for that.
Yeah, well, actually, I have an interesting story about op-amp intuition and paper. In oil exploration, I was designing a data acquisition system, and the question was what ratio of open loop to closed loop gain would you need in order to correctly acquire the data? And they had this consultant worked out a ratio, but he didn't consider the complex. He didn't consider the phase shift of it. And so, in a normal if you have a resistive feedback loop, since the phase shift is 90 degrees, you first see the phase shift, and then you see the amplitude shift, because the amplitude comes in as a second order effect. And if you have a ratio of 1,000, your amplitude only changes. Well, it's more than a part per million, but it's not a part in 1,000. But the phase shift shifts a lot, and that corrupts your ability to measure rock resistivity. It just makes it more difficult to find the oil. And so that was a case where simulation, because it didn't, it was a literal example of what was really going on. You could find out. You could make a data acquisition system, and on paper, the natural thing to do of a person familiar with the art, it would get the wrong answer.
The other thing I would do with our op amp labs, you talked about being in the benches, and again, I felt guilty about this, but in retrospect, I'm I was maybe ahead of the curve. But I would design in potentiometers into all my op amp circuits so that instead of just popping in onto my breadboard the actual value I wanted, I would always use a potentiometer so I could dial it in, and that saved me a lot of time. Can you talk about the early days of LTspice, maybe the first version and kind of what that was like to roll out?
Okay, yeah. The very first release of LTspice outside of Linear Technology Corporation that is released without an NDA was in late October of 1998. We had all the field application engineers, all the FEEs and Milpitas, and they all got a CD with LTspice, and they were set out to install LTspice on drive down the road and install LTspice on customers' machines. So that was in 1998, and it was 10 months after I had started writing it. And it had the whole schematic capture, simulator, waveform viewer, marching waveforms, cross-probing, the whole thing was there.
10 months is
and then after that, you just have to hold it in a state of zero outstanding bugs for a year or two, and we had it.
10 months is a wildly short amount of time in my mind for something like that. Was that your original timeline?
Well, no, there was no original timeline because Linear Tech didn't want LTspice. They wanted a piece of sales collateral that would shoehorn customers into some solution that they had, which is not to disparage LTspice, Linear Tech at all. That was exactly the right management decision to make, because a company can't say, oh, we're going to write a SPICE program. It's going to have a better user experience than anything out there from any EDA company at all, and we're going to give it away for free. I mean, a company can't decide, can't make that up as their strategy,
Yeah.
That was my agenda, and because I figured I could do it. And so there wasn't a dispute, it didn't have a Gantt chart. The project didn't have a Gantt chart laid out of what was going to be done what. It was all, I was just flinging my metabolism against this high-risk project. There is a story behind it that's interesting, and that is I had help outside of Linear Technology Corporation. I had 3 personal friends who I called on the cell phone every day. I had their cell phone numbers, and I would cycle through them to not put the burden on too much. One guy, the guy was really helpful, was a guy who did database internals. He didn't write databases. He would actually implement the database code. So he knew computer science better than any other human being I've ever met. Okay, I mean, this guy was one of the best software developers in California. He just happened to have been a personal friend of mine, and he told me things about replacing data with procedure. So in your waveform viewer, you don't actually have the data; you just have a procedure to replicate it. And all these, if it's database seems boring, but if you ever type in something in Google and you instantly come to what you're looking for, there's a technology to that. Okay, and he knew all that technology, and I used. He was my source of true computer science. And then the other 2 guys, one was pure GUI. He knew, the library, the Windows library exceedingly well. Actually, he kind of thought it as an end to itself. He would use Microsoft framework, and he figured it was almost like a religion. He wouldn't say that, well, this is what they did, but this is what you want. And, you can go beyond that. So he knew everything. He knew every library call. He knew every bug in the library, and I could just, I didn't have to spend 3 days figuring out what was going wrong. I'd get the answer in 20 minutes later. And the third guy was a cross between these 2. He knew object-oriented programming extremely well, and the GUI, and knew how they meshed together. So he helped me organize classes that would straddle the Microsoft GUI classes with what I was trying to do. So it was an important pedestrian architectural viewpoint thing. So yeah, I had 3 friends that, and I had the cell phone numbers, and I would cycle through calling them. And that meant I didn't have to spend very much time staring at a computer, wondering, reading the same line of code over and over again, wondering why I wasn't doing what I was doing.
That is the worst part of programming.
And that's why And that's why I was able to do it in 10 months. And nobody can write a code like that in 10 months. It's impossible. Unless you actually don't waste a minute.
Yeah, that is just an absolutely wild timeline. Why do you think LTspice has had such staying power? And are there any moments when you look back on the history of it, that you're most proud of?
The staying power came from, the user experience, and that I wanted people to have an experience like they would have, that they would understand, that you would, like scoping it out on the bench. Like you'd have your circuit board, and you wouldn't label a node and then plot something by that label. You just point at it with your oscilloscope and point at it. It was very important to me that nodes did not have to be labeled. And CAD tools before then didn't understand that. The labels should be invisible. You don't think of the label. You don't when you have a board, when you have your first artwork back and you have it stuffed and you want to see if it works and you scope it out, you don't think of the names of any of the nodes. You think of the topology of the circuit, and you just point at it with an oscilloscope probe. And that experience was rather unique to LTspice, and that's what I did. So they could understand what it was doing, and I think that experience is the right one. Whether you have you have this baggage of scoping out circuits on the bench or not, it's still the right experience to have. That's one reason. The other reason is different cat. The other reason is the guy who wrote it, myself, was with the project for so long, so I could maintain it, and I could maintain it without getting into any C-level people's hair. I could it took care of itself, in the sense that the guy who wrote it took care of it, and it wasn't a problem after that.
Yeah, it was.
So that's what I think, that was its staying power.
Self-contained in a way, where like you were the ultimate owner of it, in terms of responsibility and maintenance. Yeah,
in terms of responsibility.
In 2020, I understand we're now faced with a new SPICE simulator. Can you talk about QSPICE, how it came to be?
Well, QSPICE, I started at January 1, 2020. That's when I downloaded the open source code. It used to be that all you had to do, I would love to just be an analog engineer. Analog engineering is beautiful. It's interesting. It's kung fu. You feel empowered when you design these circuits, and it's great. But unfortunately, everything today has some digital. So QSPICE is a phenomenal mixed mode simulator. You can just draw a box, type in some code. QSPICE will compile that code to native Intel object code and execute that code during the simulation. So what happens is, when you simulate in LTspice, the digital part actually evaluates faster in simulation than it can in the hardware. Unless you put a Pentium processor in your hardware, it will simulate faster than the hardware. So that's a big deal, and allows you to present an arbitrarily large amount of digital logic to your SPICE simulation. And that reflects the fact that simulation requirements change. So that's one thing it does. But I'm a little ahead of myself there. The real thing, the real way to make a better SPICE program is just start with a fresh lobotomy. Go back to the open sources, refactor the code in the way you wish you would have done it, and do that. So that's what I did, and I found I found bugs in the Berkeley SPICE code I don't think you can find by any other way. Unless you're extremely familiar with the code and then refactor the code so it will compile in a modern compiler. There's bugs in there. It's common knowledge that SPICE doesn't work very well if you have 20,000 transistors. You'd think it's sufficiently complicated code that that could happen. Who knows the specifics? It's just a bug in the sparse matrix package.
Interesting.
It just has a hard time with it. You might be able to do it, but you will start having problems because of just a bug in the sparse matrix package that occurs at about 4 different places. And you'll never find that bug unless you start with a fresh lobotomy, look at the open source codes again, and refactor it anew without making changes to just get it to compile, but actually looking at what it's doing. So QSPICE has that benefit. I fixed a lot of IV curve discontinuities. So the reason why SPICE can solve circuits is because it can analytically iterate to the solution because the IV curves are continuous in value and slope. So SPICE seems to be doing the impossible. It seems like it's solving the arbitrary nonlinear system, which is exactly what's impossible. But it's actually solving a very specific example of the arbitrary nonlinear system, and that's one where all the IV curves are continuous in value and slope, so you have hope of being able to analytically iterate to the solution. And it uses a phenomenally fast way of iterating. It's basically like the FFT of iteration. This Newton iteration sounds like a big contraption, but it's the fastest way to iterate. It's phenomenally fast. You only need a few iterations to get the answer correct, as many digits as you want. So it's redone code. It's a better SPICE program. If you just give it some bipolar, some net list of transistors, it will solve it more reliably and faster than prior art. Plus, it's a phenomenal mixed mode simulator. It will you can literally put an arbitrary amount of nonlinear of digital logic in your simulation, and it will not impact the speed of your SPICE program. So that's what it does, and it's responding to the fact that simulation requirements change, and it's responding to the fact that I think this will survive beyond my actual horizon.
How does that feel to know it's going to, outlive your professional career?
I honestly don't care.
Yeah,
I figure when
fair.
I'm punched out. I just honestly don't care.
I love that.
It's just, to me, it's just lot and parcel of doing what I'm supposed to do now.
Yeah, that's fair. How long did this one take to build? I have to assume it was longer than 10 months.
Yeah, it took. It's taken over 3 years. It's complete. It's done. You can stick a fork in it, but development is still going at a flat-out breakneck speed. I'm still working. If I'm awake, I'm working on QSPICE. That's the way it's going. That's the phase that it's in right now.
Yeah, that's almost a freeing place to be, because for me, when I'm in that mode, I know everything I could possibly do is being done on that project, and the rest is kind of, how the lots fall. Keynote speakers and live sessions for EE Power Day are brought to you by Mouser Electronics. As your design fulfillment distributor, Mouser is your authorized source for millions of components from over 1,200 leading brands. Come discover, design, develop.
People wonder, well, if you're doing this, you must not have a life. And it's like, no, you don't understand. I mean, when I started refactoring the Berkeley SPICE code, looking at code I'd seen 20 years ago, I could remember who I was seeing in those days. I could remember what my cats were doing. I could remember where they were sitting. I relived years of my life when I did that. It was just an enthralling experience that I don't think I've ever felt so alive as when I started over with new codes. It was just an amazing experience. I think other people aren't living. It was really a beautiful experience.
Interesting. It's like an unlock for those early days. But now you're coming at it with a known success rate of the things to avoid and the things to focus on. How has that, almost doing a 2.0 changed your vision going forwards with this one?
You have to pick strategies when you refactor code to make it maintainable and compilable in modern compilers. And these strategies change because the hardware changes and the theory changes. Those new numerical methods that are known now that weren't known 25 years ago. Compiler theory advances. SPICE is basically a compiler, and I'm using newer compiler theory in its implementation. So, yeah, I'm using newer compilers too, but the SPICE itself is a compiler. And then I use new compiler theory when I implement it. So that helps.
That makes sense. It's almost like when you draw components and you build a circuit to be simulated, that's almost your input code. And then the SPICE is compiling those basically code blocks under the hood, I have to assume.
Well, the CAD part turns it into a netlist, and the netlist is basically a programming language. So you have all the same parsing stuff to parse that netlist, put it in data structures, and then either implement object code or interpret sections of it. And having seen so many SPICE simulations I've known where to do what.
There's a lot of matrix math involved here, and I imagine hardware now is different than it was in 1998 when this released. Can you talk about, the growth of GPUs and even like NPUs?
You can implement a SPICE program or an analog circuit simulator that uses the GPU for its internal calculations. It's probably more effective for evaluating IV curves than actually doing the matrix, but you can get a speed up there. However, the GPU doesn't have the potential accuracy of a CPU does. A CPU will have has a native 80-bit floating point, which is quite useful in places. You can't redo every single algorithm so it isn't sensitive to numerical round-off. You have to live with some as the way they are. You can't find every single one of them. So just using extended precision is very useful to critical in having a robust SPICE program. And a GPU can't do that. So yeah, you can make a SPICE that uses the GPU. You can publish some benchmarks that show some improvement, not that much, not like, how many floating processors you have, but you might get, 40% faster, maybe a factor of 2 on some circuits, who knows. But it won't be as robust of a SPICE program. So I'm not a fan of using GPUs for SPICE simulation. I don't think that it's a good way of going, no matter how many benchmarks you have that show that you can get a signal out of. So in QSPICE, I use the GPU and I use it extensively, but what I use it for is for plotting waveform data, because a GPU can plot lines 100,000 faster than a CPU. It does this by using the technology that was developed for teenagers' video gaming needs. I mean, when you're in a video game, you need to draw a lot of triangles, and they'll rate the CPU or the GPU by how many triangles per second you can draw. Well, if you want to draw a line, just draw it as 2 triangles that make a rectangle. That's a line. And since that technology is exceedingly fast, you use that gamer technology to draw your lines. And that's a big deal because, one, the lines are dithered, so it doesn't look like a Pong game. You actually have a smooth, artist's drawn line. And the other thing is that it's extremely fast, and you don't have to compress the waveform data. You can actually plot the data from the SPICE program. So for the first time, I have a SPICE program that shows you every single computation it did, because compressing waveform data can give you a factor of 40, but I got a factor of 100,000 from my GPU. So ultimately I heavily use the GPU here, but there's nothing fancy here. I'm using technology of what it's supposed to be used. I use the CPU for computation, the GPU for drawing lines, and that's what I recommend. There's really nothing fancy here. That's what it's doing.
Yeah, that makes a lot of sense when you put it out that way. I just assumed, in today's world, everything's running GPU heavy, but to use it for that, but not the other computation, it seems...
Well, I don't know that everything is running GPU heavy. I mean, there's a couple of problems with making everything GPU heavy. It's not everyone has, a gamer GPU in their PC. If you want it to run on any machine or any notebook, you want to be careful with what you do with the GPU. Now, with the advent of I believe it was Windows 10, all of a sudden the GPU became required. You couldn't run the operating system without a GPU, and that GPU will draw lines fantastically faster than a CPU. And so I still can use the technology even if your notebook only has some, Celeron processor in it or something. As long as it's running, Windows 10, or 11, I have enough GPU there for my purposes.
The name is QSPICE instead of LTspice. LTspice is linear technology. QSPICE, I assume the Q is for Qorvo?
Yes.
Can you describe that relationship for me?
Well, they own it. It's not that complicated. I started developing the simulator on January 1, 2020, but I wrote it because I knew I would sell it, or my goal, the business plan was to sell it. And so it originally was just called a proper name from antiquity. I called it SPQR for the ancient name for Rome. and I gave it all non-trademarkable names. All the little pieces that had non-trademarkable names, so that once it found its forever home, the owner could give it its names. So that's the flow there. I developed it under names drawn from antiquity, and then when I sold it to Qorvo, and that dealt with Jeff Strang. Jeff Strang and I had known each other a while, and he's always seemed like a person that could look at fundamentals and make decisions on principles. And it was very easy to be honest with him, and we confided what we thought the value of QSPICE was. And long story short, the deal closed. Qorvo owns QSPICE.
So you built it to be almost a branded commercial product of sorts, but QSPICE is free. How did the decision come to be to make it free like LTspice was?
Well, it's more free than LTspice. So
Okay.
the thing is, so Qorvo's interest in making it free is to expand awareness that Qorvo has a lot of cutting edge power products. Qorvo used to sell to only a few very large customers. In the interest of diversifying, they want a broader recognition for what they do. And QSPICE was a good way of doing that. Everybody would have heard of. I think everyone's heard of QSPICE at this point. So their motivation was to increase awareness of the fact that they are a cutting edge power product provider. As far as it being free, it's really free. Competitors can use QSPICE.
Sure.
If you read the LTspice license, competitors are not allowed to use it. You can't use it in house.
Interesting.
You can't promote your products with it. It's just not allowed. Though some companies have an agreement where they can. Like I think the first one, there's some companies that sell like power transistors, and this is okay. We can distribute models of our power transistors, but there's no such agreements like that I know of for any controller product or any IC, anything that competes with ADI. So QSPICE is the opposite of that. Competitors are welcome and even encouraged to model their controllers in QSPICE. There'd be so much, they should too. I mean, it's so much easier. I've modeled very many hundreds of ICs, and it would take a couple of weeks for me to make an IC model in LTspice, and then it wouldn't necessarily run very fast because it might have 100 gates and flops in it. In QSPICE, you can just write the code in C++ or Verilog. It'll run easily 100 times faster, and it will only take you a few % of the amount of time to develop the model as it will in LTspice. So, with QSPICE, it's actually reasonable to expect that one competent individual can make all the models that any old S&P 500 semiconductor manufacturer would need for their products. So it'd be fantastically cheaper to use QSPICE. They're welcome to do it. They're encouraged to do it. I'll help you get started. And, that's a big difference. QSPICE is the only simulator that's universally available to everyone. That's new.
That's a beautiful thing, and it's powerful. And I imagine it's beneficial for Qorvo too, as someone who's sat inside an enterprise org that has changed names at least twice without changing the core offerings. That level of brand awareness I'm sure is helpful, but it's also incredibly helpful for engineers when it comes to power simulation and actually using QSPICE. Do you have any tips or things that engineers might not be making the most use of that you think they should look at?
There's a huge range in SPICE users' ability and all that. So it's hard to give a boilerplate suggestion. But if you need to ask, then what I would recommend is to learn how to master the .step command. The .step command allows you to overlay simulation results changing one component. So that's your, potentiometer in your circuit. You try the same circuit with different resistor, capacitor, or inductor values, or some other, maybe you change some gain. So that will let you master. If you master .step, there you're really doing exactly what you need to develop an intuition of a circuit. The other thing I would recommend is to draft very neatly. You will. It's good to draft neat. If you learn to draft neat, you won't be confused with what you're doing.
That's smart.
So that would be my advice there.
Yeah, I know early on in my circuits were always kind of a mess, but I definitely learned after getting stuck because I made a silly mistake somewhere. Keeping a clean layout is is a really important thing that you don't realize how important that is until later.
The analogy I use there is this. You can tell a good software developer because if you look at his code, the logic of the algorithm would just leap off the page and be able to immediately read it. You don't need to read every single variable name and all this. You'll understand what he's doing simply because it's formatted and expressed on the page well enough. You can understand what it's doing. And again, and with analog circuit design, you want the circuit design so that what you're doing, the rationale of your circuit just leaps off the schematic and you can see it.
In college, we're not often taught much, at least I wasn't, about, like silicon carbide, high power, gallium nitride, like these big high power components that are now becoming pretty mainstream. What advice do you have for folks who are starting to work with these and trying to simulate, high power tools instead of just low power analog or digital?
Well, the main thing you should do is just run a lot of simulations. You're not going to blow up the computer if you put 4,000 amps through a transistor.
Yeah.
So just simulate everything that you can think of. Just simulate everything. And there's kind of two sides to what you're asking about. One is the new semiconductor technology and the and moving from academic small signal education, which may or may not exist, and actually trying to design analog circuits. If you're just going to try to design analog circuits, then what I gave is the right answer. For the new transistor technology, you have to be aware that newer transistors are actually a bit electrically different than older types of transistors. Gallium, a GaN FET isn't wired up the same way as a normal FET. Okay, there's no body diode. So normally, if you have a MOSFET or a power MOSFET is typically a vertical device, or in any case the body diode. It might be a substrate diode if they actually print it as a lateral. But you have a forward diode conductivity if you bring the drain negative to the source. You don't have that in a GaN FET unless the gate is connected to the source. If the gate is connected to the source and you bring the drain negative, well, Mother Nature doesn't know the difference between the drain and the source. It's just the drain. The active source is whichever is more negative. So if you bring the drain negative, it's the source, and the gate is tied to the drain. And if you bring the drain now source sufficiently negative, you have enough threshold voltage there, and it conducts. So if you look at a half bridge, it looks like you have a body diode, but what's happening is that it conducts at the threshold voltage instead of the PN junction. So you do need. There's a little bit of extra knowledge you need to move to the newer types of transistors because they're actually wired internally differently.
Yeah, that would be a surprise to find out in the real world.
Yeah. Of course, the GaN models in QSPICE do know how they're wired differently, and I've changed the device equations to support the newer wide bandgap devices because they really are wired differently inside. For like the silicon carbide FETs, there's two ways of making a silicon carbide FET. One is as a MOSFET, but it's kind of better. Well, it is better to use to make a JFET device because of you get a much lower RDS on. You can have the RDS on if you use a JFET in silicon carbide instead of a MOSFET. Of course, the problem with a JFET is that it's normally on. If you short the gain to the source, it's as on as much as possible. And which is not what you want in a traction inverter or most power devices. You want if the driving circuit is turned off, you don't want the power transistors turned on. Okay, so the solution there is to include a low voltage MOSFET with a negligible RDS on, and it's called the cascode configuration. The gate of the JFET is shorted to ground, shorted to the source of the MOSFET, and you can control the transistor with the MOSFET gate, but you get the RDS on of the JFET. It's a cascode device, And that's a native circuit element in QSPICE. I call it the level 2010 MOSFET. It's actually a Cascode device with all the internal inductances to from the bonding wires of the two dice connected together.
Yeah, a little bit of best of both worlds there, I would say. Can you talk a little bit about like boost caps and how they might be helpful, or maybe time domain, frequency domain? I've heard you talk a little bit about that as well.
Okay, good. So
yeah.
if you're new to power and you want to learn how to do power, one of the most important things to understand is the high side end switch, and it needs a boost capacitor in order to. Okay, so the thing is, if you're high, okay, end switches are better than P switches because they always have less RDS on. Whether it's a bipolar or a MOSFET, that's the situation. They have a lower RDS on for the same reason. Electron mobility is higher than hole mobility. So you want both switch. You want to only use an end polarity switches if possible. Now, if you have a high side end switch, then you have to, in order to fully turn the thing on, you have to pull the gate well above the source, but the source is at the input voltage, which means you need a voltage above the input voltage. To do that, use something called a boost cap, which bootstraps the high side gate driver above the input voltage. And it's pretty simple. If you use a monolithic controller, it all pretty much just happens for you automatically. Though you may need to add a diode from a logic level to the boost cap, so to make sure that when the switch node is ground, you charge up the boost cap. So when the switch node goes high, the boost cap is bootstrapped up with it. But you need to understand the boost cap. It's a bit of magic there, and a lot of people in electronics, if you're just coming from generic circuit design or circuit analog stuff, you might not be aware of this very simple idea, which is important. But you need to charge the bootstrap cap. You need to know if the controller has the algorithm to refresh the charge on the cap if it ever goes away, because a lot of controllers have to monitor that voltage. If you're going to strategically not switch the top switch because you don't need to, you might lose boost cap voltage, and you have to refresh the charge somehow. You just need to understand how that thing works and why you can use an end polarity on the as a top FET. And I think that everyone who gets into power sort of have this, once they come into fully understanding this thing, it's like a spiritual experience. They finally understand how the whole power supply works. Yeah. Once they get that. Now the other thing is that if you want to get into power simulation, I would advocate that you do a lot of time domain analysis. Frequency domain analysis is what you learn to do in school, and it's what you do if you don't have a simulator. But for a lot of modern power supply, a lot of times, if you make the simplifications to look at this nonlinear circuit as some low-frequency linear circuit, you've actually decided to throw away the issues that can make the thing oscillate. So you have to look at it in the time domain. And if you get experienced enough at looking at the time domain, it's not that hard to get to a point where you can get 10 times as much information from a time domain analysis than you can from frequency domain analysis, and the time domain analysis also runs 10 times faster. So frequency domain analysis of switchboard power supplies is a pretty serious losing game, and it's stressed too much in academia. I think that you really need to move away from it and look at everything in time domain. There's a cultural thing here. In some companies, everything is time domain. In some cultures, everything is Bode plots. But I'm from a culture that's moved beyond the Bode plot and outgrew them.
When you look at the roadmap for QSPICE, where is this going? What's next?
I usually don't tell people what's next. And the reason is, if I don't, then I can undertake projects with a great deal of technical risk. Okay? And I do that. I've taken on projects, and I realize this is just too hard. I can't finish it. I sure am glad I didn't tell anybody. So I don't tend to tell people what I'm doing ahead of time. There's one thing I'm very excited about now, and it's all I can do to not tell you about it, because I still just I need to finish it before I tell people what it does.
We'll have to wait and find out.
Sorry about that.
That's okay. A little bit of mystery. Yeah. I'll be watching the news now. Well, we're out of time. Thank you so much for being here.
Well, I really do appreciate your interest. Hey, the thing is that the only thing I do for a living is QSPICE. So your interest in QSPICE actually means, in any final analysis, that your interest in QSPICE is a matter of life and death to me. It's the only thing I do for a living.
Well, I would not be here if it were not for your tooling. So thank you so much. That was Mike Engelhardt from Qorvo. And this was the last Moore's Lobby episode for Season 7, but we're already working on Season 8, so we will be back. As always, please share this podcast with other folks that you think will enjoy it, and come say hi to us on the Moore's Lobby and All About Circuits social media pages. But most importantly, and this may sound cheesy, but I really mean it, thank you for tuning in. It truly is an honor to have you as a listener. Moore's Lobby was produced by Tara Gledhill and Dale Wilson, and I'm your host, Daniel Bogdanoff, and I'll catch you right back here for Season 8.